Hello, I'm Michael, and I'm here to explore Diffeology, the hidden math that's changing everything. In mathematics, a diffeology on a set generalizes the concept of a smooth atlas of a differentiable manifold by declaring only what constitutes the smooth parametrizations into the set. A diffeological space is a set equipped with a diffeology. Many of the standard tools of differential geometry extend to diffeological spaces, which beyond manifolds include arbitrary quotients of manifolds, arbitrary subsets of manifolds, and spaces of mappings between manifolds. Diffeology, the hidden math that's changing everything, introduces the fascinating world of differential geometry and its surprising applications. The differential calculus on Rn, or more generally, on finite-dimensional vector spaces, is one of the most impactful successes of modern mathematics. Fundamental to its basic definitions and theorems is the linear structure of the underlying space. The field of differential geometry establishes and studies the extension of the classical differential calculus to nonlinear spaces. This extension is made possible by the definition of a smooth manifold, which is also the starting point for diffeological spaces. A smooth n-dimensional manifold is a set M equipped with a maximal smooth atlas, which consists of injective functions, called charts, of the form letter 3D5. U right arrow M, where U is an open subset of Rn, satisfying some mutual compatibility relations. The charts of a manifold perform two distinct functions, which are often syncretized. They dictate the local structure of the manifold. The chart letter 3D5. U right arrow M identifies its image in M with its domain U. This is convenient because the latter is simply an open subset of a Euclidean space. They define the class of smooth maps between manifolds. These are the maps to which the differential calculus extends. In particular, the charts determine smooth functions, smooth maps M right arrow R, smooth curves, smooth maps R right arrow M, smooth homotopes, smooth maps R2 right arrow M, etc. A diffeology generalizes the structure of a smooth manifold by abandoning the first requirement for an atlas, namely that the charts give a local model of the space, while retaining the ability to discuss smooth maps into the space. Diffeology, the hidden math that's changing everything, introduces a fascinating concept, and now we'll delve into an informal definition. A diffeological space is a set X equipped with a diffeology, a collection of maps P. U right arrow X U is an open subset of Rn, an n greater or equal to 0, whose members are called plots that satisfies some axioms. The plots are not required to be injective, and can must have as domains the open subsets of arbitrary Euclidean spaces. A smooth manifold can be viewed as a diffeological space which is locally diffeomorphic to Rn. In general, while not giving local models for the space, the axioms of a diffeology still ensure that the plots induce a coherent notion of smooth functions, smooth curves, smooth homotopes, and so on. Diffeology is therefore suitable to treat objects more general than manifolds. Diffeology, the hidden math that's changing everything, introduces a fascinating concept that's reshaping our understanding of the world. Let M and north be smooth manifolds. A smooth homotopy of maps M right arrow N is a smooth map H. R times M right arrow N for each TR, the map HT, equals HT. M right arrow N is smooth, and the intuition behind a smooth homotopy is that it is a smooth curve into the space of smooth function C infinity. M, N, connecting, say, H0 and H1, but C infinity, M, N, is not a finite-dimensional smooth manifold, so formally we cannot yet speak of smooth curves into it. On the other hand, the collection of maps P, U right arrow C infinity, M, N, the map U times M right arrow N, R, X, P, R, X is smooth, is a diffeology on C infinity, M, N. With this structure, the smooth curves, a notion which is now rigorously defined, correspond precisely to the smooth homotopes. Mathematics has always been a powerful tool, and now, Let's explore its surprising origins with history. The concept of diffeology was first introduced by Jean-Marie Sauerreau in the 1980s under the name espace differential. Sauerreau's motivating application for diffeology was to uniformly handle the infinite dimensional groups arising from his work in geometric quantization. Thus, the notion of diffeological group preceded the more general concept of a diffeological space. Sauerreau's diffeological program was taken up by his students, particularly Paul Donato and Patrick Iglesias-Zemmer, who completed early pioneering work in the field. A structure similar to diffeology was introduced by Quotients Chen, Chinese letter, Chen Guokai, in the 1970s, in order to formalize certain computations with path integrals. Chen's definition used convex sets instead of open sets for the domains of the plots. The similarity between diffeological and Chen structures can be made precise by viewing both as concrete sheaves over the appropriate concrete site. Diffeology, the hidden math that's changing everything, introduces a fascinating concept that's reshaping our understanding of reality. A diffeology on a set X consists of a collection of maps, called plots or parametrizations, from open subsets of Rn. For all n greater or equal to 0, to x such that the following axioms hold, covering axiom. Every constant map is a plot. Locality axiom. For a given map P, you write arrow x if every point in U has a neighborhood V U such that PV is a plot, then P itself is a plot. Smooth compatibility axiom. If P is a plot, and Fahrenheit is a smooth function from an open subset of some Rm into the domain of P, then the composite Pf is a plot. Note that the domains of different plots can be subsets of Rn for different values of n. In particular, any diffeology contains the elements of its underlying set as the plots with n equals 0. A set together with a diffeology is called a diffeological space. More abstractly, a diffeological space is a concrete sheaf on the site of open subsets of Rn, for all n greater or equal to 0, and open covers. Mathematics has long been a silent force, but now we're beginning to uncover its surprising influence on the world around us. A map between diffeological spaces is called smooth, if and only if its composite with any plot of the first space is a plot of the second space. It is called a diffeomorphism if it is smooth, bijective, and its inverse is also smooth. Equipping the open subsets of Euclidean spaces with their standard diffeology, as defined in the next section, the plots into a diffeological space X are precisely the smooth maps from U to X. Diffeological spaces constitute the objects of a category, denoted by Diffeology, whose morphisms are smooth maps. The category Diffeology is closed under many categorical operations. For instance, it is Cartesian closed, complete and cocomplete, and more generally it is a quasi-topos. Mathematics has long held secrets, and now we're diving into the fascinating world of topology. Any diffeological space is a topological space when equipped with the topology, the final topology such that all plots are continuous with respect to the Euclidean topology on Rn. In other words, a subset Ux is open if and only if P, U is open for any plot P on X. Actually, the topology is completely determined by smooth curves. That is, a subset Ux is open if and only if C, U is open for any smooth map C. Our right arrow X, the topology is automatically locally path-connected. A smooth map between diffeological spaces is automatically continuous between their topologies. Therefore, we have the functor D, Diffeology right arrow top, from the category of diffeological spaces to the category of topological spaces, which assigns to a diffeological space its topology. This functor realizes Diffeology as a concrete category over top. Mathematics has long been considered abstract, but diffeology reveals a surprisingly practical and powerful approach to problem-solving. A Cartan-de-Ram calculus can be developed in the framework of diffeologies. as well as a suitable adaptation of the notions of fiber bundles, homotopy, and so on. However, there is not a canonical definition of tangent spaces and tangent bundles for diffeological spaces. Mathematics has been quietly shaping our world for centuries, and now diffeology, the hidden math that's changing everything, reveals its surprising influence. Any set carries at least two diffeologies, the coarse or trivial or indiscrete diffeology, consisting of every map into the set. This is the largest possible diffeology. The corresponding d-topology is the trivial topology. The discrete or fine diffeology, consisting of the locally constant maps into the set. This is the smallest possible diffeology. The corresponding d-topology is the discrete topology. Any topological space can be endowed with the continuous diffeology, whose plots are the continuous maps. The Euclidean space Rn admits several diffeologies beyond those listed above. The standard diffeology on Rn consists of those maps P, U right arrow Rn, which are smooth in the usual sense of multivariable calculus. The wire or spaghetti diffeology on Rn is the diffeology whose plots factor locally through R. More precisely, a map P, U right arrow Rn, is a plot if and only if for every UU there is an open neighborhood VU of U such that PV equals QF for two smooth functions F, V right arrow R and Q, R right arrow Rn. This diffeology does not coincide with the standard diffeology on Rn when n greater or equal to 2. For instance, the identity Rn, right arrow x equals Rn, is not a plot for the wire diffeology. The previous example can be enlarged to diffeologies whose plots factor locally through RR, yielding the Rankar-restricted diffeology on a smooth manifold M. A map U right arrow M is a plot if and only if it is smooth, and the rank of its differential is less than or equal than R, for R equals 1 recovers the wire diffeology. Diffeology, the hidden math that's changing everything, introduces a revolutionary approach to understanding complex systems. Diffeological spaces generalize manifolds, but they are far from the only mathematical objects to do so. For instance, manifolds with corners, orbifolds, and infinite-dimensional Frachet manifolds are all well-established alternatives. This subsection makes precise the extent to which these spaces are diffeological. We view DFLG as a concrete category over the category of topological spaces, top via the d-topology functor D. DFLG right arrow top. If U, C right arrow top is another concrete category over top, we say that a functor E, C right arrow DFLG is an embedding of concrete categories. If it is injective on objects and faithful, and D, E equals U, to specify an embedding, we need only describe it on objects. It is necessarily the identity map on arrows. We will say that a diffeological space X is locally modeled by a collection of diffeological spaces E if around every point XX there is a D-open neighborhood U, a D-open subset V of some E, and a diffeological diffeomorphism U right arrow V. Mathematics has long been a hidden force, shaping our world in ways we don't always realize. The category of finite-dimensional smooth manifolds, allowing those with connected components of different dimensions, fully embeds into DFLG. The embedding Y assigns to a smooth manifold M the canonical diffeology P. U right arrow MP is smooth in the usual sense. In particular, a diffeologically smooth map between manifolds is smooth in the usual sense, and the d-topology of Y, M, is the original topology of M. The essential image of this embedding consists of those diffeological spaces that are locally modeled by the collection Y, letter 211D, N, and whose d-topology is Hausdorff and second countable. Mathematics has long held secrets, and diffeology is unlocking them to reshape our understanding of the world. The category of finite-dimensional smooth manifolds with boundary, allowing those with connected components of different dimensions, similarly fully embeds into DFLG. The embedding is defined identically to the smooth case, except smooth in the usual sense, refers to the standard definition of smooth maps between manifolds with boundary. The essential image of this embedding consists of those diffeological spaces that are locally modeled by the collection Y. O is a half space, and whose D topology is Hausdorff and second countable. The same can be done in more generality for manifolds with corners, using the collection Y. O is an orthant. Mathematics has been quietly revolutionizing fields from finance to medicine, and now we'll explore the foundational concepts of Freichet and Banach manifolds. The category of Freichet manifolds similarly fully embeds into Diffeology. Once again, the embedding is defined identically to the smooth case, except smooth in the usual sense refers to the standard definition of smooth maps between Freichet spaces. The essential image of this embedding consists of those diffeological spaces that are locally modeled by the collection Y. E is a Freichet space, and whose D topology is Hausdorff. The embedding restricts to one of the category of Banach manifolds. Historically, the case of Banach manifolds was proved first by Hayne, and the case of Freichet manifolds was treated later by Lossick. The category of manifolds modeled on convenient vector spaces also similarly embeds into Diffeology. Mathematics has long held secrets, and now we're beginning to unlock them. A classical orbifold X is a space that is locally modeled by quotients of the form Rn/gamma, where gamma is a finite subgroup of linear transformations. On the other hand, each model Rn/gamma is naturally a diffeological space, with the quotient diffeology discussed below, and therefore the orbifold charts generate a diffeology on X. This diffeology is uniquely determined by the orbifold structure of X. Conversely, a diffeological space that is locally modeled by the collection Rn/gamma, and with Hausdorff D topology, carries a classical orbifold structure that induces the original diffeology, wherein the local diffeomorphisms are the orbifold charts. Such a space is called a diffeological orbifold, whereas diffeological orbifolds automatically have a notion of smooth map between them, namely diffeologically smooth maps in Diffeology. The notion of a smooth map between classical orbifolds is not standardized. If orbifolds are viewed as differentiable stacks presented by étale proper Lie groupoids, then there is a functor from the underlying one category of orbifolds and equivalent maps of stacks between them to Diffeology. Its essential image consists of diffeological orbifolds, but the functor is neither faithful nor full. Mathematics has long been a secret language, but now diffeology, the hidden math that's changing everything, is revealing its profound impact on the world. If a set X is given two different diffeologies, their intersection is a diffeology on X, called the intersection diffeology, which is finer than both starting diffeologies. The D topology of the intersection diffeology is finer than the intersection of the D topologies of the original diffeologies. Mathematics has long been a secret language, but now diffeology, the hidden math that's changing everything, is revealing its profound impact on the world. If X and Y are diffeological spaces, then the product diffeology on the Cartesian product X times Y is the diffeology generated by all products of plots of X and of Y. Precisely a map P. U right arrow X times Y necessarily has the form PU equals XU YU for maps X, U right arrow X and Y, U right arrow Y. The map P is a plot in the product diffeology if and only if X and Y are plots of X and Y, respectively. This generalizes to products of arbitrary collections of spaces. The D topology of X times Y is the coarsest delta-generated topology containing the product topology of the D topologies of X and Y. It is equal to the product topology when X or Y is locally compact, but may be finer in general. Mathematics has long been a secret language, but now diffeology, the hidden math that's changing everything, is revealing its profound impact on the world given a map F. X right arrow Y from a set X to a diffeological space Y. The pullback diffeology on X consists of those maps P. U right arrow X such that the composition Fp is a plot of Y. In other words, the pullback diffeology is the smallest diffeology on X making F smooth. If X is a subset of the diffeological space Y, then the subspace diffeology on X is the pullback diffeology, induced by the inclusion X left arrow curving right Y. In this case, the D topology of X is equal to the subspace topology of the D topology of Y if Y is open, but may be finer in general. Mathematics has long been a quiet force, but diffeology is revealing its surprising power to reshape our world given a map F. X right arrow Y from diffeological space X to a set Y. The push-forward diffeology on Y is the diffeology generated by the compositions Fp, for plots P. U right arrow X of X in other words. The push-forward diffeology is the smallest diffeology on Y making F smooth. If X is a diffeological space and is an equivalence relation on X, then the quotient diffeology on the quotient set X/ is the push-forward diffeology induced by the quotient map X right arrow X/. The D topology on X/ is the quotient topology of the D topology of X. Note that this topology may be trivial without the diffeology being trivial. Quotients often give rise to non-manifold diffeologies. For example, the set of real numbers R is a smooth manifold. The quotient R/Z plus alpha letter 2124, for some irrational alpha called the irrational torus, is a diffeological space diffeomorphic to the quotient of the regular 2 torus R2/Z2 by a line of slope alpha. It has a non-trivial diffeology, although its D topology is the trivial topology. Mathematics has long been shrouded in complexity, but diffeology is revealing a surprisingly elegant and powerful approach. The functional diffeology on the set C, infinity, X, Y of smooth maps between two diffeological spaces X and Y, is the diffeology whose plots are the maps letter 3D5. U right arrow C infinity, X, Y such that U times X right arrow Y, U, X, letter 3D5, U, X, is smooth with respect to the product diffeology of U times X. When X and Y are manifolds, the D topology of C infinity, X, Y, is the smallest locally path-connected topology containing the Whitney C infinity topology. Taking the subspace diffeology of a functional diffeology, one can define diffeologies on the space of sections of a fiber bundle, or the space of bisections of a Lie groupoid, etc. If M is a compact smooth manifold, and F right arrow M is a smooth fiber bundle over M, then the space of smooth sections gamma, F of the bundle is frequently equipped with the structure of a Freychit manifold. Upon embedding this Freychit manifold into the category of diffeological spaces, the resulting diffeology coincides with the subspace diffeology that gamma, F, inherits from the functional diffeology on C infinity, M, F. Analogous to the notions of submersions and immersions between manifolds, there are two special classes of morphisms between diffeological spaces. A subduction is a surjective function F, X right arrow Y between diffeological spaces such that the diffeology of Y is the push-forward of the diffeology of X similarly. An induction is an injective function F, X right arrow Y between diffeological spaces such that the diffeology of X's, the pullback of the diffeology of Y subductions and inductions, are automatically smooth. It is instructive to consider the case where X and Y are smooth manifolds. Every surjective submersion F, X right arrow Y is a subduction. A subduction need not be a surjective submersion. One example is F, R2 right arrow R, F, X, Y equals XY. An injective immersion need not be an induction. One example is the parametrization of the figure 8. $F, left, frac pi2, frac 3 pi2 right to math bar 2 quad ft equals 2 cos t sin 2t. An induction need not be an injective immersion. One example is the semicubic. F r right arrow r2 ft equals t2 t3. In the category of diffeological spaces, Subductions are precisely the strong epimorphisms, and inductions are precisely the strong monomorphisms. A map that is both a subduction and induction is a diffeomorphism. Mathematics is revealing surprising connections through diffeology, a concept poised to reshape our understanding of the world.